Hello, my name is Grace Su. This summer I worked on mixed reality synthetic data generation. My mentors were Srinivas Narasimhan, Kim Vuong, and Dinesh Reddy. One of the most ubiquitous challenges in developing computer vision models is obtaining realistic, accurately labeled, diverse, and large computer vision datasets. This is because it's difficult, time-consuming, and expensive to acquire and label real-world data. Additionally, data is often characterized by a long-tail distribution. Synthetic data generation can help address these issues because it automatically computes new images that imitate real-world data distributions. These new images can then augment existing datasets and potentially train more robust computer vision models. One of the exciting applications of synthetic data generation is that we can simultaneously generate the 3D ground truth data. In particular, synthetic data generation would be especially useful for training deep learning models for traffic analysis tasks like vehicle segmentation, object tracking, and 3D pose estimation. Prior works have proposed several different synthetic image data generation methods. However, each of the methods include one or two of the following limitations. Their synthetic data is not photorealistic, so that may cause sim-to-real domain adaptation issues. In addition, some proposed data generation methods have relatively high computation costs. There may also be a lack of fine control over scene generation parameters. Finally, there's a lack of evaluation of employing synthetic data for vision tasks other than object segmentation. Thus, the objective of this research is to investigate whether a mixed reality method can generate synthetic, realistic road scenes and facilitate the training of computer vision models. In our method, we choose to use Mitsuba, a physically based renderer that photorealistically renders 3D vehicle models. We also take measures to ensure that the scene parameters we use as input are realistic. Then after rendering, we can compose rendered vehicles onto existing real-world photos by using pixel-wise computation methods described by previous work. Here is an illustration of our proposed synthetic road scene generation method. Our method takes scene parameters as input in order to match the appearance of the desired background photo. Then, those scene parameters are used to render 3D vehicles in Mitsuba. We render the following images for each road scene to obtain the necessary images for final image composition and depth maps. The road plane with the 3D car models, the 3D car models only, and the road plane only. We also render the individual depth maps for each car model, where each pixel's value is its ray distance from the camera. Finally, we use the previously mentioned image composition method to produce our final output, the composed image. The composition method ensures the car shadows are added and blended into the background photo. From the individual depth maps, we can also compute an array representing the entire scene's ground truth segmentation labels in the future. The advantages of our method compared to previous work are the following. It produces physically accurate photorealistic road scene images. It provides precise 3D and geometric ground truth labels. It takes advantage of real-world priors to improve data fidelity to the real world, and it grants a high degree of control over scene generation parameters. The following images are preliminary results produced by our method. Here's an actual image output produced using our method. All cars in the image were rendered and inserted. Here's another example where we have an example of a real traffic camera photo with one rendered vehicle inserted. The rendered vehicle is actually the black SUV that's second from the bottom of the image. As you can see, its appearance is consistent with the real cars and the scene geometry. So for our future work, in addition to refining our mixed reality synthetic road scene generation method, we plan to generate rare scenes. These include generating scenes containing rare objects or object configurations. Then we can evaluate whether using rare scenes can improve the training and robustness of object detection models. Some useful rare objects we could render include uncommon vehicles. And here is an example of a rare object configuration where we have an anomalous traffic pattern. Our other plan for future work is to conduct experiments in training amodal segmentation models, which aim to predict the object's full segmentation mask despite visual occlusions. Specifically, we plan to evaluate whether synthetic data and precise depth maps produced from our method can improve the training and performance of amodal segmentation models. So in conclusion, our mixed reality method for synthetic road scene generation produces photorealistic results. Our method can also generate images and ground truth labels for a variety of computer vision tasks. In particular, synthetic data generation could potentially provide valuable 3D ground truth data for vision tasks that predict 3D world information from 2D image data. Thus, this research work will allow us to discover how synthetic data generation can augment existing vision datasets and consequently train more robust computer vision models. Here are the references for this presentation. I would like to thank the CMU Illumination and Imaging Lab and the Robotics Institute Summer Scholars Program for their mentorship and support.